Okay, hello everybody. Um, we have um, one person on Zoom. I hope you can hear me. So we stopped last time on the word to vec, and the plan for today is to show you the code to finish this first week presentation, and also uh, to talk about dimensionality reduction, t-SNE. So last time we stopped on the loss function um, for word to vec, and as you remember, the idea was that we take the sliding window with central word and um, calculate the probability to find to meet another word, the gray one, in this sliding window that contains our central word. And typically, the sliding window has size 5, 10 words. Then, this was our loss function. Then we said that we take gradient descent, so we take one element at a time. So the question is how to actually create the vectors for these words. The answer is just initialize by random numbers. So in code, I want to show you. Or it's here. So in code, we just create the embedding layer. So who took the machine learning class should remember that embedding layer just creates a matrix with random numbers. And the size of this matrix is here. So typically we have just indices. And in our case, these are indices of our words in our dictionary. And then it creates for every index, for every word, in other words, the embedding of the size embedding dimension. So if we have, for example, 50,000 words in our dictionary, this matrix will be of size 50,000 by the embedding size. And we create two embedding layers, one for central words, another for the context words. And so this is how these embeddings are created in practice. So let's go back to slides. So now you understand what does this dot product mean. We just take the vectors, the embeddings, and take the dot product. And so we stopped on the negative sampling. So let's go to the negative sampling. Um, so this is our loss function for one word. When we take log, then we have numerator and minus denominator. And as you remember, the denominator sums over all the words in our dictionary. And negative sampling says that we can sum over just few words instead of 50,000 or 20,000, we can sum over just 20 words, for example. So, okay, here it is. The idea of negative sampling was um, to update our probability for uh, one word pair. And you remember in softmax, when we increase one probability, all other probabilities will decrease. So we will decrease only few probabilities. So this is the idea of this negative sampling. So we will increase the probability of the numerator, but we will decrease the probabilities only for few words. And instead of going through the entire dictionary, we will go just through K words. And why it's so? First of all, it will be very efficient because if we don't use this trick, then it will be the same time-consuming as count-based methods. So that's why this model actually became popular because of the efficient training. But how to justify this idea? So why we can decrease the similarities only of few words instead of the entire dictionary? What do you think? What is the justification? So I didn't mention that these keywords, they sampled randomly, well, according to just frequency of the words in the probability or in our dictionary, but they sampled from this probability distribution randomly. And why it's fine if it decrease the similarities with just random sampled words. Yep.
Probably gives about the same results, but it saves a lot of time because you don't have to use the whole vocabulary.
Yeah, but why we will decrease the similarity? If you think about the sliding window, the context of every word contains, I don't know, maybe 100 words. The size of dictionary is thousands. So if you sample randomly a few words from this 50,000 words, most likely they will be out of the context. So this is one justification that we can do this. The other idea is that you go through all word pairs, and if you didn't decrease the similarity for other the size of dictionary minus k words, maybe you will decrease this on other step of your gradient descent. So still you will go through all the data and maybe several times epochs. Okay, so this is a justification. And then our loss function will look like this. Numerator and minus the, instead of sum over all words, just over k sampled words. So I will skip this. So if I can show you how it's implemented in code. Yeah, so this is actually the entire code. So we take the dot product between a central word and context words, and also we create so-called negative scores between central word and other k sampled words. And there are also a few other functions that so this is the distribution that was proposed in paper. The distribution from how we will actually sample these keywords. And U is the frequency of our words in the dictionary. And I don't know why they used this power 0.75, but maybe it worked better. So this is the distribution for sampled words. And also there is also another trick. They drop very frequent words. So, and that's it. So just with these two tricks, you can train word embeddings. Let's go back. Do you have any questions about the model?
Do we have access to this notebook?
I can, yeah, I can. Well, you don't, but I can,
Okay.
I can upload this on this week. Yep. So we will use the built-in model for next class. Bring your laptops because it will be coding, and we will use like in machine learning we had NumPy and scikit-learn. NumPy, where we just wrote our code. In scikit-learn, we used the ready models. So there are ready models. So we will use NLTK library as NumPy, and we will use JSIM library as scikit-learn, where word2vec is implemented, and you just pass your data, and it returns the word embeddings. I mean, this code is not won't give you maybe a very good word embeddings because it's just studying code, but in library it will work better, of course. So yeah, let's go back to presentation. And there is one modification of the word2vec, which is called cbol, and the difference is that in word2vec we calculated similarity for gray words with the context word. In the other model, they calculate the similarity of the central word with gray words and just sum these dot products together. But word2vec has better actually scientific justification. So typically people use word2vec. And there is another, let's see, well, some details that the number of words that we use in our softmax is typically 20. The size of embeddings is between 100 and 300. People try to use 1000 length for embeddings because they thought that maybe more parameters will provide better result. But after a lot of trials, they came up with 300 as the optimal size for embeddings. And the sliding window about 5-10 words from each side. So if we choose so this slide demonstrates the difference between large and small sliding window. So if we use large sliding window, then these embeddings will learn some general semantic. So if we use smaller sliding window, then the embeddings, the words will be grouped by syntax. You can see that they have similar endings, for example. So larger context tends to keep more general information. And these parameters, sliding window, you also can choose in the built-in models. So today we'll have two very important ideas. And this is the first of these two important ideas in NLP and in general in machine learning and in science. So we talked about a count-based approach, when we can just count the co-occurrence of the words and put in vectors. And we said that these methods are used because if we want complete explainability of the model. And then we talked about a neural network model, where we just initialize randomly vectors, and then we minimize something, and then we get some embeddings, and then they have some nice properties, but it's hard to explain. So there was a paper in 2019, there is a link that demonstrates that these two approaches, the embeddings built by count-based methods and neural network methods, word-to-vec, will coincide, like if we will continue training of word-to-vec infinitely. And this is very interesting because many people argue that large language models are missing explainability, but maybe in 10 years, like with word-to-vec, we will actually understand that what they actually converge to. And today we will see also, and we will see a lot of these examples, like in PCA, principal component analysis. You can think about this as dimensionality reduction, or you can think about statistical interpretation or geometrical interpretation, and they all three give the same result. So the same is here. Another model, GloVe, actually combined these two approaches. So in count-based, we had information from statistics of the words, and then we applied singular value decomposition. In word-to-vec, we didn't calculate statistics, we just applied our model, generated the embeddings. The GloVe model combined these two ideas. So this is the loss function for GloVe model. So it uses the counts, like in count-based models, the counts of frequencies of word and context. But at the same time, it trains embeddings. And it trains embeddings. You can see that if you don't look at the bias terms, this function minimizes the difference between counts and embeddings. but also they use some factor. Again, it's empirical function. I don't know how they come up with idea of this function. So this function can just gives smaller weight for less frequent works. So if the frequency is under some threshold, then this coefficient is small. Maybe for stability of training. Okay, so this is another model that you will hear. Now let's talk about evaluation of these models. There are two types of evaluation. One is intrinsic and the other one is extrinsic. Intrinsic means when we use the model itself to evaluate, for example, and extrinsic when we use other models or experts to, or benchmarks to evaluate the model. And I can think, so if I evaluate myself intrinsically, I can think that I'm a very good lecturer, but then I read the reviews after class, and then I can see opposite actually evaluation. So the same with models. And of course, it's better to use extrinsic evaluation, but sometimes you don't have time to run other models to evaluate the model. So yes, this is what I said, that we can look if our model captures the similar meanings of the words. And for extrinsic, we can use the word embeddings, for example, for a text classification task or for another task, and see how these embeddings work for a new task. And yeah, as I said, the problem with extrinsic, it may be time consuming, and but it's better maybe evaluation. Now the last topic for lecture, and where we will talk about second very interesting and important idea, and then we will talk about dimensionality reduction. I hope we'll have time. So I want to ask you to open this NLP course for you link. Of course, if you want to, and just play with these embeddings and check how words are grouped together. So where is our... So you will find the link on week 1. Here is the link, NLP course for you. And the first topic is word embeddings. You can go to read more. And in the end of this work page, there is this plot. And you can look at how words are grouped together using this. So they use GloVe. Well, let's yeah, play a little bit, and if you find some interesting like clusters, if you find something interesting, then share with us. For example, if you think that two words shouldn't be grouped together, but they are in the same cluster.
Interpreting the data.
Oh, well, so our similarity. Oh, you didn't see how actually to see the rows.
Interesting.
So I hope you could see that the words grouped by some similarities, but did you find some interesting words that group together that you didn't expect that they would be grouped together? What did you find there?
So near that big cluster on the left.
Yes.
There's like the tiny two dots. It could probably be, but there's no yes. So if you're
Which
gonna-
words?
so
Me-
see that big cluster.
Yeah,
right there?
what words?
It was me, no, and yo. Those have no meaning together. To each other. Me, no, yo.
Yeah, so you should understand how the model was trained. So it was trained on some texts, and most likely these words were used maybe in a very close context. So maybe in this 5-word, or I don't know actually what was the window size here, window. And and you can explain this just by the corpus of text that was used for training. If you will train this on another, I believe it's trained on Wikipedia, but and in practice, we will use the actually ready word embeddings. We'll just upload these matrices with vectors and use them. Okay, so yeah, I just want to mention that all these words were grouped together, and I bet you didn't know all the names for these frogs, but the model learned, of course. I just want to say that model learns more than a human being can learn because it reads all the dictionaries, all the textbooks, and so on. Yes, there are some benchmarks that are used for extrinsic evaluation, but nowadays, yep.
I'm just noticing that some of the tokens are like apostrophe S or apostrophe VE. So it's like not full words. How does that play into the model?
Oh, we will talk on Friday about tokenization, so how to split texts into tokens, and it depends on the tokenizers. So it means that you just split it by apostrophe and it created a new token. Yeah, so I just want to say that now benchmarks, actually people use large language models to generate data sets instead of collecting data sets. Another interesting thing was the linear dependency between these embeddings. And I'm sure you've heard about this. So when we take the embeddings for king and subtract the embedding for man and add embedding for woman, then we will get a vector which is close to embedding of queen. And you can play with that also on this course. Let's see, where is it? Have fun. In Have Fun, you can actually play with adding and subtraction words and guess what will be the close word embedding. But you can do this later. Now let's go back. And when people notice this linear dependency, it was just a nice feature, but again, several years ago, after discovering this, there was mathematical proof that these word embeddings actually have linear properties. Also interesting linear dependencies between countries and capitals. So, for example, what does it mean? It means that if you add to a word embedding of China something and get Beijing, then to any other country, for example, Italy, you can add the same vector and you will get Rome. So this is an interesting idea. This is for word to vector. That is for GloVe. GloVe is not very linear. Okay, I think what else? Similarities. Oh, the second really unexpected and interesting observation, the similarities across languages, because now we were talking about similarities of words inside language, but what about different languages? So if we train word embeddings for different languages, and then try to rotate somehow the embeddings for one language such that to match few words, typically 100 words, for example, got and cat, what, how, I guess, I don't know. Then all the other words also will be matched. It's a very unexpected idea. That if you just match, and you will do this in your first homework, if you match just few words in different languages, all other words also will be matched. What does it mean? What do you think? I don't know, maybe philosophically. Huh?
That a lot of concepts are associated the same. It doesn't matter what the language it's spoken is.
Yes. Yeah, it looks like you remember in first class we talked about meaning of words and surface representation, and I said that it's hard to formalize the meaning. It's something that we can't define, but it looks like this meaning actually similar across different languages. Okay, so now let's go to the second, or maybe more, yes, let's go to the second part of today's lecture.
Is that true for like almost every language?
It's a good, yeah, it's a good question, and actually the answer is on this course, like for word embeddings, and there is extra reading. So the idea is, so the answer is that the rotation works for similar languages like Italian, Spanish, or Slavic languages, Russian, Ukrainian. The problem that I gave you for homework English and Spanish, and you will see, because they're different, they have what's called the articles. So the translation won't be very good, but Yeah, so for closer languages, the structure, this semantic structure of words will match better. There is another paper that you can add also shrinking, not only rotation, and then it will actually match even different the language from different groups, but it won't be just linear transformation. So I have prepared, you will find this notes on the first week. So I don't know, did somebody take a look at these notes on PCA, t-SNE? No? So, so here's the reminder of PCA and how we obtain dimensionality reduction from minimizing the distance between points in one space and in another space. And then there is a proof, if somebody wants to read, that Lagrange multiplies, that it equals to the result will be actually the sum of total variance. And then there is connection with statistics, where I proved that actually these Lagrange multipliers will be the variances, and geometric interpretation that the PCA is the projection of our vector onto the new on the principal component space. But today I want to talk, and here are some illustrations. If we project this cross in one dimension, if we subtract one dimension, then we will get the plane, we will get two-dimensional, the residual will be two-dimensional. Then we can project to two-dimensional space. If we subtract this from our data, residuals will be one-dimensional, and finally we can project to three-dimensional without any losses. Yeah, today I want to talk about t-SNE. Also, I think the most popular method for dimensionality reduction. So here is the paper where it was proposed. I believe it's 2003, something like that. So what is the problem with PCA? If our data set has like two clusters, but PCA actually will choose the principal component along these clusters, and after projection, these data points will be mixed. And here is the illustration of principal components. If we use t-SNE, we will talk now about what does perplexity mean. Then you can see that with different parameters of perplexity, we have better separation of these points. And that's why in this plot with vectors, they use t-SNE, because the idea of this method is that to keep the distances between objects, if the vector embeddings were close in 300-dimensional space, they will be close in two-dimensional space. Okay, so let's talk about the idea of t-SNE. Let's say we have a point X. A point X And then we can find the distances from this point to all other points in our data set, like in k nearest neighbors, and then sort these points by the distance. And for example, then we can introduce the probability distribution as follows. We can assign the probability 1 over k for k neighbors and zeros for other points. Let's calculate the perplexity. So the definition of perplexity is 2 power entropy. So do you remember what is the entropy from machine learning class? We talked about entropy in decision trees. Yes.
Measure of uncertainty.
Yeah, but I mean the formula. It's negative. So it's it's negative. So the definition is that it's expected value of information, but information is the log of probability. So it will be information is negative log, sorry, of probability. So it will be negative, then sum, for, I don't know, for I, pi na log of pi. So let's calculate perplexity for our 1 point. So if we assign, so we have 1 point x xi, and we have k points close to this one. So and we calculate the probability for distance between these points. Let's indicate this probability as I1 under condition I as 1 over k. Also, we set the probability that points with index I2 close to I also as 1 over k, and so on. And probabilities that points with index k greater than k plus 1, okay, we'll just set to 0. So let's calculate the entropy and then perplexity. What will be the perplexity in this case? How many non-zero points, how many non-zero probabilities will we have? K. So the sum will be from 1 to k, and it will be the probability will be 1 over k times log of 1 over k. And we should sum over k, so the sum goes from I to k, so it will be just negative log of 1 over k. And when we take 2 power entropy, what will we get?
Minus 1 by minus
2 power negative log of 1 log base 2.
minus
Okay, so perplexity of the paired die is equal to the number of faces. You will get k because because 1 over k is negative log of k. Okay, so I just wanted to that you understand that perplexity stands for the k nearest points in this case. What if, so in this t-SNE, they said, okay, instead of looking at k near, just k nearest points, we can introduce the Gaussian distribution with some variance. And we choose variance such that k points will be in the center of our Gaussian. So instead of 1 over k, they use this distribution, the Gaussian distribution with some parameter c. And in the model, you remember the parameter was perplexity. So you can think about this as the number of points that we take into consideration, but in the model, based on this perplexity, actually the sigma will be calculated. Okay, so after we introduce the probability of one point to be a neighbor of another point, we introduce another probability on the two-dimensional distribution. And then we minimize Kullback-Leibler divergence, and that's it. So this is the idea of this is how the gradient we calculate, and here is the result of PCA for NIST data set, and here's the result for t-SNE on NIST data set. You can see that digits are separated much better using t-SNE than PCA. But if we increase perplexity, so we take more neighbors into consideration, then you can see something a little bit weird, that one cluster was actually separated, which is the number 5, separated by 8, something like that. Okay, I think we can stop here. And next time when you will use t-SNE in homework or in practice, you will understand the parameters, like what does perplexity. Okay. Yes, that's it.
Ideal perplexity should.
It's a hyperparameter, so it's kind like you can just try different. The question was which perplexity to choose. The recommended perplexity between 5 and 50. But here, for example, 50 didn't work well.
I need to go to that.
Yeah, I think honest, I don't know how you make what is you wrote. Yeah, but I saw that.
Yeah, it really because I was using it to do plots for one of my paper things, and it makes things look good globally, but it doesn't actually put their time. Like things that will look close to them, they're kind of in the font and actually close to one another unless they're in a cluster.
Yeah, it stands for universal manifold, something like that. Yeah. Thank you.